Okay, so this is starting a new unit. It's still in chapter 8, but we've already tested over 8.1 and 8.2. We're still doing a little bit with polar form, but we're getting into complex numbers. So remember with your complex numbers, you have an A and a... My computer has been giving me a little bit of trouble. Hopefully I'll make it through the video, but if you can't read something, just let me know. You have A plus BI, where A is your real and B is your imaginary, but B is just the coefficient. You won't include I. So we're going to be graphing these complex numbers. Here's an example of what that looks like. So here's your real axis, which would be like your x-axis. That's where you're going to graph your A. Here's your imaginary axis, which is like your y-axis. This is where you're going to graph your B. And so if I were to graph, let's make a complex axis here. So here's our real and here's our imaginary. And if I wanted to graph z1, so 2 plus 3i, I would go over 2. That's my A, my real. And there is 3i. And that's where z1 would plot. If I wanted to plot z2, I would go 3 and a negative 2i. And that would be z2. This asks for z1 plus z2, which means I'm going to need to add them together. What is 2 plus 3? What is 3 minus 2? So z1 plus z2 is 5 plus I. And if there's no number there, we know it's a 1. Now, if it looked just like, say, let's say z sub 3 was 6i, what that would look like is it would look like 1, 2, 3, 4, 5, 6. And there would be no real component to it. Here your A would be 0. And your B would be 6. But here your B is 1 because it's understood to be with that I. And you'll see some on your homework where it asks for this, which is multiplication. So you would multiply these two, FOIL them out. And we've done that before with complex numbers. Don't forget that I squared is a negative. So you can just simplify that and graph. Okay, so this graphing looks a bit different. We're graphing the sets, so you can see our set notation here. It says the set S, where A plus BI is what we're defining it in, which means it's going to be a complex number such that A, which is our real component, is greater than or equal to 0. We're still going to have our real and imaginary, but, and that's what that tells us, right? It tells us it's complex. We have an inequality, which tells us two things. We need to check dotted or solid, and we need to check shading. This has a solid line under it. It's an or equal to, so it's going to be a solid line. And we are going to shade greater than. We want a line that is greater than or equal to 0. Remember, A is kind of like your x. And so this is going to be a x equals something line, which is a vertical line. So I'm going to have a vertical line at 0. And again, it's solid because it's the or equal to. And then I want to shade where it's greater than, which is going to be the right. And that's that. If that were a B is greater than or equal to, it'd be a horizontal line. So A is like your X, so it's vertical. B is like your Y. Remember, Y is wide, so it's horizontal. This one's a little bit more complicated. We still have a set. We still have imaginary or our complex numbers. So I'll label it such. A is less than 1. So remember, A is going to be your vertical. It is not or equal to, so it's going to be a dotted line at 1, and it's everything less than that. Then we have B, which is going to be horizontal, is greater than or equal to 0, so it's solid at 0, and we want everything greater than. But my answer is where the two overlap, which is most of quadrant, or it's all of quadrant 2, but it also goes a little bit into quadrant 1 right there, all the way up to 1. And that would be the yellow would be your final answer. You do not have to shade both regions if you just want to shade the final answer, but somehow I need you to distinguish what the final answer is. This is not new. We did a little bit of modulus for our argument, it can be called, or absolute value when we did some trig with polar equations. This is how we denote the modulus. You'll also see it called R when it represents our argument. This should be familiar to you. This is Pythagorean theorem, and that's what we're doing. This represents the distance. So this is our modulus, it's our distance, it's our argument. All of those are, sorry, I have no clue why it's doing that. Writing like that, sorry. This is our argument. So remember, we take our A and our B, we're not going to use our I. So for the first one here, A is 3, B is 4, and we're just going to do Pythagorean theorem. So our modulus is going to be 3 squared plus 4 squared, which you should recognize the 3, 4, 5 triangle. And that's our modulus. That's all. So this point is, which is a point, right? That goes back to what we graphed in number 1, is 5 units away. If we were to do this, which I ask you to pause this and work this on your own and then check your answer, consider this to check your progress. Okay. So if you did this, don't forget a negative square is a positive, and you can type this in your calculator and get the decimal equivalent, but you just need to play that and you're good. Okay. So now we're going to graph again, but this time we're graphing, see the modulus, and that absolute value is the modulus, and remember that's the distance. So what this is saying is graph the modulus, which is our distance, is 1. So the distance from the origin is 1. I want you to think about what you can graph where every point is 1 unit away from the origin. Hopefully you know that would be a circle. So if I, from my origin, 1 unit away, 1 unit away, 1 unit away, 1 unit away, that would also be 1 unit away. And you could keep doing that and it would be a circle. So what the modulus is telling you is it's your radius. Okay? Modulus is telling you how far away it is from the center, which is always going to be your radius. And so that's the answer to A. On B, it's the same thing, except it has this absolute value. So it's still saying the modulus is 1, which means my radius is 1, but it's saying anything less than or equal to 1. So we know it's solid. If it's less than 1, it could be 0.5, it could be 0.25, so it's going to be inside. I want you to pause it and work and graph this right here. Okay, so take a second, pause it, and work this one. Okay, so this is a radius of 3, and it's everything greater than that, so it's on the outside, and it's not equal to, so it's dotted. I have a really hard time drawing a dotted circle, so I always have to draw my circle and erase it. But that is what it should look like, so just be careful for shading. And your dotted are solid. Remember the difference in this is that it's telling us to graph the modulus, which is going to be your radius, and this was telling us to graph just something in the complex, which means these are lines. You might see something say like that. Remember your A is like your X and your B is like Y. So if that helps, you can always just solve for Y. And you would be graphing a line with a slope of -1 and a y-intercept of 5. So if that helps you to call them x and y instead, you know how to graph those. Okay, so this is just an equation. It's like a standard, it's like a standard form, and it looks a little rough, but really we're just mostly plugging in. We're going to find two things. We're going to find the argument, which we already talked about, and then we're going to find theta. Now this says tangent theta is equal to b over a. We did this last section and called it, we solved for solved for theta, which is the inverse tangent of y over x, but remember y is like b and x is like a. So those are the two things. Remember, you might have a different answer based off of 2 pi. So like you could say negative pi over 4, or you could add 2 pi to it, and there's multiple answers, and so that's totally fine. Also, if it doesn't tell you degrees or radians, it's fine to do either. I prefer radians, but degrees is totally fine. Just if you're using degrees, make sure you include the degree symbol so that we know. So I'm gonna work One is easy. Let's start with one and we'll work C. And I think you should be good on everything else. So A is 1 here. B has an understood one. So when I'm finding R or the argument or the modulus, it's going to be the Pythagorean theorem. And then when I'm finding theta, it's the inverse tangent of B over A, 1 over 1, which is the inverse tangent of 1. Where is the tangent 1? It's at pi over 4, or 45 degrees. So now all I need to do is plug into that formula right there. And this is a little counterintuitive. You are literally just going to plug in. So I'm going to have cosine of pi over 4. Most people forget their I. There's a mistake on this. That's the number one mistake made. It's just forgetting that. Now, normally you'd say, okay, I know the cosine of pi over 4. I know the sine of pi over 4. Yes, you do, but this is standard form. You leave it like that. That is all you do in your done. Let's do C, and then you'll have some practice ones for homework that you can always check your answers to. But I'm sure you're good to go on this. So that is A. B is -4. When I find my R by doing Pythagorean theorem, I'm going to have both of them negatives, which when they're squared they become positive. -4 squared is 16. Square root of 3 squared is 3. 16 times 3 is 48. If in doubt, you can type that in your calculator. And okay, and then you get 48. And you can it doesn't say to leave this in exact form, but okay, sorry about that. It doesn't say how to leave it, but you do want to leave it as exact as possible. I give the square root of 64, and you know that's 8. Now I need to find theta. Inverse tangent of B over A. Our negatives cancel, our 4's cancel, and we get that. So we want to say, where is my tangent? 1 over 3. Oh, you basically have two options, 30 degrees or 60 degrees, 5 or 6 or 5 or 3. And if you'll just kind of pick one and start looking at it, if I found the tangent of this, I would do y over x. And you can see that that would reduce to that, which is what I have. So that is my answer for theta. And so now I just need to plug it into the form. And so z equals r cosine theta plus I, don't forget that I, sine theta. And that's your answer. So you have about 20 homework problems due tomorrow. But first, there's something I need you to look at. So some of the equations we've been looking at are for fractals. I need you to read this. I need you to get a good idea of what fractals are. And so give me a good definition of fractals. You'll find that somewhere down in here. And I also want to know some examples of where you can find fractals. And then go back and you're going to watch our video on fractals just to kind of see these are computer generated fractals. Also, that's a good name to know. He's the big name as far as fractals go. So finish the rest of the assignment on Schoology, and we'll pick up there. You can do homework, and I'll take questions tomorrow.